Hello and welcome to the webinar on hardware-in-loop testing of battery management system using Simulink Real-Time and Speedgoat hardware. My name is Chirag Patel. I'm an application engineer at MathWorks, and I focus on helping customers move from desktop simulations to real-time testing. I am joined today by my colleague Javier Gazari, who is a principal application engineer at MathWorks and focuses on everything related to batteries and battery management system. In this webinar, we are going to show you how you can use MATLAB and Simulink to design and test battery management system algorithms. In the first part of this webinar, we will show you example models of BMS algorithms and test them in desktop environment with the help of a detailed plant model of a battery pack. In the second part, we will use battery cell emulator hardware and Speedgoat real-time target machine to test BMS controller in real time. Before we get into the details, let's quickly look at how the final test setup looks like. This is the picture of our hardware setup. We used a laptop as a host computer. MATLAB, Simulink, and other development tools are installed on this computer. We use Simulink to design and implement various algorithms for an example battery management system and tested the functionalities of these algorithms using a detailed battery pack model created using Simscape library. Using desktop simulations, we can test BMS algorithm during different operating modes such as discharge during drive cycle, charging, and balancing during non-operation mode. Here we can see effect of battery current on individual cell voltages, state of charge, and cell temperature. We will study these models in detail in a few minutes. After successful desktop simulation, we deployed the BMS algorithms onto a embedded target along with a required peripherals for measuring cell voltages and currents. Now we need to test functionalities of embedded target, or commonly called ECU, in real time with all physical peripherals including fault conditions more thoroughly. To perform this test, we have two choices. We can either use actual battery pack and perform various tests by cycling battery pack through different charge cycles and thermal operating envelope. Well, this is not only expensive and time consuming, but sometimes it can be limiting in terms of what type of tests can be performed with the actual battery pack. The second option we have is to use a hardware setup which allows us to emulate the dynamic behavior of battery pack programmatically in a controlled and safe manner without connecting it to actual battery pack. The second approach is called hardware-in-loop testing, where a plant model is deployed onto a real-time target machine to emulate the behavior of a physical system and produce feedback signals such as cell voltages that embedded controller can read from. For this setup, we use real-time target computer from our partner company Speedgoat to execute our plant model in real time and a battery emulator card IO991-06 from Speedgoat to produce isolated cell voltages. With that, I will turn over to Javier, who will explain us the common BMS architecture and how we can use MATLAB and Simulink to design and test battery management algorithms.
Thank you, Chirag. We are looking at the top level of a BMS model where we see input control components to select different functional scenarios, indicators of possible fault states, and a model reference containing the BMS algorithm and the battery pack. On the left-hand side, we use a source block to stimulate the system with different usage cycles and tests. The system itself comprises a model reference representing the BMS ECU with its various monitoring and control algorithms connected to a block with the representation of the battery pack and associated circuitry and peripherals. The battery pack is either a small 6-cell series or a larger 16-module pack, each module comprising a 6-cell series string. We call these architectures 6S1P and 96S1P packs, respectively. Let's start with a description of the battery pack and its peripherals. The variant subsystem on the left contains two versions of the battery pack mentioned earlier. Let's describe the 6S1P version first. The 6 cells are connected in series and also exchange heat with one another. The thermal layout is asymmetrical, with cell 6 insulated on one side and cell 1 convecting heat to the outside. Inside each cell, there is an equivalent circuit representation with parameters calculated using isothermal discharge experiments and parameter estimation. A detailed account on how to perform the estimation of these parameters is available on our website, Searching for Battery Modeling. Next to the battery pack, there is a subsystem with the passive balancing circuitry. Commanded by the balancing logic from the BMS algorithm, these switches selectively close when their corresponding cell needs a partial discharge to lower its SOC. A further element of the plant model is the set of charger and inverter contactor circuitry. Prior to connecting a battery pack to a charger, it is important to pre-connect them via a resistor to prevent an excessively high current from rushing into the pack and potentially damaging it. This pre-connection needs a special sequence that we will show when we describe the BMS algorithm. Finally, the last piece of the battery plant is the charger and the load, both simply represented here by current sources commanded to follow the charging and driving profiles from the source block at the model top level. Let's now focus on the BMS algorithm. The subsystem on the left uses individual cell voltages and temperatures to calculate maximum allowable charge and discharge current levels. When a cell is at low SOC, its voltage is low, and it is important to prevent the cell from delivering a large amount of current, since this would cause an excessively large voltage drop that could potentially be below the cutoff voltage specified by the cell manufacturer. Comparing the minimum cell voltage in the module against this lower threshold and dividing it by the maximum internal resistance value calculated for this cell, we compute a voltage-based current threshold. We also know that it is important to limit current delivery or intake when temperature is too high or too low. Using a lookup table with a rising or falling hyperbolic tangent profile, we can specify current threshold based on temperature. These two thresholds are then compared against one another, and the lowest becomes the current limit. The same procedure is repeated for the discharge. The subsystem labeled state machine defines the main operating state of the BMS. The state machine comprises 4 parallel states. The first one defines the variable BMS state, which indicates standby, driving, charging, and fault. Charging comprises constant current and constant voltage stages. The second state switches the fault state on in case of a current, voltage, or temperature value reaches an unsafe level. The third and fourth states define the contactor on and off switching sequence for the charger and inverter. This is needed to avoid an excessively large current inrush at the beginning of the charging stage. The third subsystem contains 3 different methods for state of charge estimation. In practice, the BMS developer would only choose one of them, but here we present all 3 to illustrate their individual merits and limitations. The first method, known as Coulomb counting, consists of integrating the current that enters and leaves the cell to keep track of the state of charge over time. A benefit of this method is its simplicity and very low computational cost. Its drawbacks include the accumulation of current sensor error and its inability to recover from an erroneous initial condition because of the lack of feedback from voltage measurements. The second and third SOC estimation methods implemented here are the unscented and extended Kalman filters. Both are variations of nonlinear Kalman filters, and they rely on a model of the unit cell to predict the terminal voltage resulting from a current stimulus, estimating the internal cell states, the SOC among them, by comparing this prediction against the measurement of the terminal voltage. The choice between EKF and UKF is typically made based on the severity of the system's nonlinearity. In this case, the only nonlinearity present is given by the OCV-SOC relationship, and it is a mild one, so it is expected that the EKF should give adequate results. The battery cell model used in the Kalman filter consists of two parts: the state update and measurement update. The state update predicts the current state based on the previous state value and the input, and the measurement update corrects this prediction using newly acquired data. The cell model we use is implemented as a MATLAB script and corresponds to the equivalent circuit we use to simulate the battery pack. The next task to consider is balancing. It is important to keep individual battery cells roughly at the same state of charge. Otherwise, the cell with the highest SOC level will limit the amount of charge that we can put into the pack, rendering the system underutilized. This state logic calculates the voltage difference between the highest and the lowest cell voltages and, based on whether this difference exceeds a design value, activate passive balancing. Balance command is a Boolean vector that indicates which bleed resistor to activate so that the cell SOC is slowly reduced. Doing this with all cells but the one whose SOC is the lowest eventually makes all SOCs converge within a prescribed tolerance. Looking at the simulation results from an example driving, charging, balancing sequence, we first observe the individual cell voltages corresponding to an initial SOC of 75%. Towards the end of the simulation, the values converge towards one another due to the balancing procedure. Secondly, we observe that the current is derated during charge because the maximum module cell voltage is high enough compared to the prescribed 4.4 volt limit that an excessively high current could drive the voltage beyond the threshold, significantly limiting the life of the battery. Since we calculate the current limit based on the maximum resistance value within the battery cell lookup table, we're being conservative. A less conservative current limiting calculation could use the actual battery cell resistance at the estimated SOC and temperature, since this information is available at all operating conditions. The temperature traces show a significant discrepancy among the hottest and coldest cell. The reason is mainly the asymmetry in the module layout in terms of thermal behavior. Cell number 6 gets significantly hotter than cell number 1 because it is thermally insulated on one side. Even when the maximum temperature reached during the simulation is not of immediate concern in terms of safety, the temperature difference exhibited here will eventually cause a much faster degradation of cell 6 compared to cell 1, leading to an undesirable unevenness in cell condition. Hence the need for active thermal management to keep thermal differences within a few degrees Celsius. The graph on the top right shows three SOC estimation traces of the same battery cell, each performed with a different method. Yellow corresponds to Coulomb counting, blue corresponds to UKF, and orange to EKF. The initial SOC in this simulation is 75%, but the SOC estimators were initialized to 80% to assess their capability to recover. It is apparent that Coulomb counting never does because it has no way to realize it is wrong due to the absence of voltage information. Both Kalman filter algorithms, on the other hand, recover from the initial error within the first hour of simulated time, with the EKF slightly outperforming the UKF. In summary, we've utilized Simulink, Stateflow, and physical modeling toolboxes to design a battery management system using modeling and simulation. Now, I'll turn over back to Chirag, who will show how to prepare this model to run in real time, connect it to hardware, and perform testing maneuvers without risking to damage the integrity of the battery.
Thank you, Javier. In this section, we are going to take a closer look into hardware-in-the-loop testing of battery management system. Extensive end-to-end testing of battery management system, including all the possible fault conditions, is required to make sure that the system behaves as expected. Doing this type of testing for battery management system can be very time-consuming. For example, before you start testing charge mode functionality, you must discharge battery pack to appropriate state of charge level. Testing a complete charge and discharge cycle for a typical electric vehicle battery pack takes hours. We're talking about days worth of testing when we include different operating conditions for temperature, state of charge, and other parameters. Additionally, reproducing design issues and fault conditions can be difficult and involves safety considerations. While doing testing with actual cells, achieving test automation, test sequencing, and report generation can be very expensive and requires a lot of resources, especially when there are many test equipment involved. Doing extensive testing with actual battery pack is required for final system integration test and functional test. But it does not make sense to do this type of testing for every software revision or design iteration. One way to achieve high confidence in your design iteration is by testing BMS controller and electronics against a simulated battery pack. This method of testing a real controller against a simulated plant model in real time is called hardware-in-the-loop testing. In HIL testing, we start with plant model of a battery pack. This is the model you may have used for testing BMS algorithm in desktop simulations. Next, we generate C code from the battery model and compile into a real-time application, which gets deployed and executed in real time by a dedicated real-time target computer. This target computer must have required peripherals to convert numerical values into physical signals, such as cell voltages and temperature. We connect peripherals of real-time computer with BMS controller to perform closed-loop testing. By replacing actual battery pack with a programmable one, we can now perform end-to-end testing of software and electronics more efficiently and safely. Now there are a few things we need to take care of before we can do HIL testing of BMS controller. First, we need to run the plant model of a large network of cells in real time at a sample time required by BMS controller. For the most common battery applications, BMS algorithms get executed between 100 Hz to 500 Hz. So, executing our battery plant model at 1 kHz in real time is more than sufficient for HIL testing. If your battery pack has fewer than 50 cells in series, achieving desired step time can be straightforward. The second challenge is related to hardware. Since we want to emulate the battery behavior of a battery cell, we need to have ways to produce isolated voltages and be able to connect them in series or parallel configurations just like actual cells. Additionally, you will require temperature sensor emulation and fault emulation as well. To understand how we can address first challenge within Simulink, let's take a look at example model. Here, we have a battery model with 16 cell modules, each with 6 cells connected in series, making it total 96 cells connected in series. Each battery cell block models electrical and thermal behavior. We use control current source to charge and discharge battery pack. And finally, individual cell voltages, temperature, pack current, and pack voltages is measured and sent to BMS controller. First step of going from desktop simulation to real-time testing is selecting a right fixed step solver. This is usually an iterative process, and we are not going into the details in this webinar. Instead, I recommend that you visit this dedicated webinar on the topic of real-time simulation of physical systems using Simscape. After following the steps described in the webinar, we have selected a local solver for Simscape network and identified number of consistency iterations to be 1. This solver settings yield desired result of 1 millisecond sample time. We also note that for certain topology, partitioning solver improve performance by reducing computational cost of simulation. This helps in achieving faster simulation rate for both desktop simulation and real-time testing. The partitioning solver converts the entire system of equation for the attached Simscape network into several smaller set of switch linear equations that are connected through nonlinear functions. Computational cost is reduced because it is more efficient to calculate solutions for several smaller equation systems than it is to calculate the solution for a one large system of equations. Now, the solver name partitioning can lead to some confusion. Just so that it is clear, the partitioning solver does not partition the model. The partitioning solver will not allow you to split the model and run on multi-core processor. There are other ways to achieve this. Simulink Real-Time automatically leverages multi-core processor by default wherever it is possible. Next, let's go ahead and execute our battery model in real time. In the interest of time, I have already built and deployed the application to the target computer by clicking on Build button. In the target object, we can notice the name of the application deployed onto the target machine, application status, sample time, and other useful debugging information. Let's start the execution of application on target machine. While simulation is progressing, we can observe signals of our interest and tune parameters. This simulation is only 10 seconds long. Once it's over, we can check if the target computer was able to execute the model at a desired sample time of 1 millisecond. By inspecting the target object, we can notice here that there was no CPU overload reported during the model execution, and maximum task execution time is well within 1 millisecond. This gives us enough margin for future model growth. As you add more complexity and details in the model, it is very well possible that you may not be able to achieve desired sample time just by selecting right solver. In this situation, specific to the battery modeling, you have few more options that you can consider. The first option is to select a right variant of battery block. Here, you can notice that by selecting a variant with a lower fidelity, you can easily gain 10 times reduction in task execution time. Another option is to select lower order dynamics of battery cell. This also helps in reducing task execution time significantly. This gain in performance is coming from reduced fidelity. Now, if your model complexity is lower, or number of battery cell in series is less than 50, it is quite possible that you don't have to do any of this optimization to achieve the task execution time of less than 1 millisecond. As we discussed earlier, the second important aspect of doing HIL testing for BMS application is to emulate sensor signals and sensor faults. For emulating cell voltages, SpeedGoat provides a battery emulator card IO991-06. Each battery emulator card provides 6 isolated channels. Each channel can supply up to 7 volts, which allows us to simulate different cell chemistries. Additionally, each channel can source up to 300 milliamp and sink up to 100 milliamp. Also, multiple I/O modules can be combined in series or parallel to achieve the required power levels. In addition to battery voltage emulation, we need temperature sensor emulation cards and fault insertion card to complete the BMS HIL setup. SpeedGoat provides various options for temperature sensor emulation card and fault insertions. In our demonstration, we have only used IO991 for battery voltage emulation. Now, let's see live demonstration for BMS HIL testing. We start with a test model which allows us to simulate battery cells and generate fault scenarios. Here in this test model, we have a small battery pack with 6 cells connected in series. To simulate a fault, we added a switch which allows us to short 2 cell terminals without any real physical consequences and test the response of the controller. We use toggle switch block to inject the fault interactively. A control current source block is used to simulate the charge or discharge current with the help of a slider block. To perform diagnostics on cell, we measure voltage between 2 cell terminals. The measured cell voltage values are fed into IO991 block, which converts these numerical values into electrically isolated voltages, each relating to individual battery cell. The output terminal of IO991-06 card are connected to an electronics board you see in the background here, which makes physical measurements of the cell voltages and communicates the information to a BMS controller, which in this case is a Texas Instrument controller board. The BMS controller performs diagnostics on cell voltages and generates a fault status in the case of over or under voltage fault, or short between 2 terminals. In this case, the BMS controller turns on the LED in the event of fault and outputs its status on a digital output port. We read fault status from the BMS controller using digital input port of IO133 to check if the controller logic is performing as per the requirement. Now let's go ahead and connect to target machine. Upon executing this model in real time, we can change the current all the way to 10 amperes to check for any over voltage fault or minus 10 ampere to check for any under voltage fault from the controller. We don't see any fault yet. When we inject a short circuit fault, we can immediately notice LED glowing on the controller board and also see our lamp in the model changing the color from green to red, indicating there is a fault on the controller. Let's look at the results in a simulation data inspector for whole experiment. We can notice small changes in cell voltages due to change in current. And one of the cell voltages dropped significantly as we triggered the fault and see the corresponding change in the fault status. In this presentation, we demonstrated how to create large system-level models to design and test BMS algorithm quickly, and engineers from different domains such as electrical, software, and thermal can collaborate using Simulink as a common design platform. We also talked about different methods to run large battery models in real time for doing HIL testing. And finally, we demonstrated how to set up HIL testing for BMS application and how it can help you gain more confidence in the design of battery management system. And with that, we thank you for your time. Thank you for listening.